All right, so in linear world, unbalanced forces were the things that ultimately caused acceleration. So now that we've talked some about angular acceleration, the question needs to be asked, what causes angular acceleration? And so the thing that causes angular acceleration is the rotational equivalent of force, which is called torque. And all a torque is an off-center force that causes rotation. All right, so a force that doesn't act around an object's pivot point, and we'll talk a little bit more about that. But we see an example of this down here. We have one case where there's a force applied directly to the center of the object, the point about which it naturally pivots, and another case where a force is applied off-center, okay, so not from its pivot. And what we're going to see is the one that's applied directly to the center, that's just going to cause that box to accelerate forward, but not rotate at all. However, the one that's applied off-center is going to cause a forward acceleration, but also cause an angular acceleration, cause a rotation as well. Because this one does not create a torque, however, this one, because it's off-center, does create a torque. So let's talk for a second about what factors affect the amount of torque created by a force. So the first one, and this one's probably the most obvious, is that the amount of force affects the amount of torque. The more force we have, that ultimately is going to lead to more torque. The second one, and if you think about opening a door or trying to pry a nail out of a board or something like that, the second one is the distance from the pivot. Okay, thinking about opening a door, it's a lot easier to push on the end of the door that's away from the hinge, away from that pivot point, because it creates more torque. And the last one is the angle between the force and the radial distance, the distance from the pivot, a line from the pivot to where that force is applied. So something that you're going to now need to think about that we didn't need to think about before is when we're talking about torques, we need to not only consider the amount of force, but also where that force acts. Okay, so that's going to be something that is a change from before. One last quick thing, torque is measured in Newton meters. Okay, that's going to be our unit, and that just comes from, as you'll see the equation in a second, we're ultimately multiplying the force by the distance, and that's what leads us to Newton meters. Mathematically, we can calculate torque using this equation here, RF sine theta, where R is the distance from the pivot to the force, sometimes called the radial distance, hence the R. F is the force, and theta is the angle between the force and the distance. So if we have a pivot on this board here that's like that, and our force is going like that, what I always think about is I always draw that radial distance, that R. My theta then is going to be this angle here between the force and that R, that radial distance. You may sometimes see this equation written like this, where it's radius times F, and then there's going to be this little symbol here which stands for perpendicular. So another way we can do this is just multiply by the component of the force that is perpendicular to that R value. So that is another way of looking at it, but usually we're just going to use this equation because that will never lead you wrong. Two important conceptual notes here from the previous equation. Number one, torque increases as the force and distance from the pivot increase. Okay, so there are two ways of increasing the torque. You can either push harder or push further from the pivot, okay, and that actually comes into play a lot in levers and other simple machines. And the other thing that's really important is torque is at a maximum when the angle is 90 degrees. Okay, we see that sine of theta term, and we know that sine of 90 is going to be equal to 1. That's when sine is at a maximum. So we maximize that torque when the angle is 90 degrees. Okay. Conversely, if we have no R value, okay, so any force exerted on a pivot is not going to result in any torque, okay? So no torque when the force is exerted on the pivot, meaning your R value is 0, and no torque when the angle between the force and the distance is 0. All right, we would call that parallel or anti-parallel. So if we have our board from the last problem here, if I exert a force there, that's not going to create any torque because it's on the pivot. If I exert a force like that, okay, that would be parallel to my R here, that would not create a torque, nor would it if I exerted a force in like that. That would be anti-parallel. So none of those situations are going to end up creating a torque on this object here. All right, we're going to go ahead and rank the following four situations that show a force exerted on a wooden plank, and we want to rank them from the most torque to the least torque. In each case, we are pivoting about this left end here. That's what that black dot is showing. So what I would look at first is I see that C has the most amount of force. It's applied perpendicular, which maximizes the force and is the furthest away. So I know that C is going to be the greatest. All right, so I'll start with that, even though I'm going from least to greatest. Then I look at D and B, all right, because the rest of them just have a force of F. D and B, the force is exerted closer to the pivot, so they're going to be less. And since D is exerted at an angle, that's going to be less than the maximum. That means that D is actually going to be my smallest amount of torque. That's going to be less than B, which is exerted at the same location, but at a 90-degree angle. And that one's going to be less than A, which has the same force, but it's exerted further away. And so there's my ranking. D is less than B, is less than A, is less than C. So for this next problem, we have a few different forces acting on a wheel here. So I'm going to label them 1, 2, and 3. We want to first calculate the torque created by each force. So we're just going to each time be thinking about RF sine theta. So for the first object, our R value is going to be 1, our force is going to be 40, and the angle here is going to be 90. I know it looks like it might be 60 degrees, this angle here. However, the key is we want to remember it's always the angle between the radial distance from the pivot to where the force acts and that force. And that angle, and you can see it's labeled right here, is 90 degrees. So the torque from force 1 is going to be 40 Newton meters. The torque from force 2 is going to be RF sine theta once again. So 1.3 is our distance for the 50. The force is 50 newtons, and the angle is going to be 90 degrees as well. So that means the torque from object 2 is going to be 65 Newton meters. Okay, and then the torque from 3, all right, we have a distance here of 1.3 because it acts on the edge, same distance as the 50 Newton, a force of 60, but our angle here is going to be 0 because the angle between that radial distance, which is going down, and that force, which is also going down, is 0. Or you could call it 180. It doesn't really matter. Either way, torque 3 works out to be 0 Newton meters. Part B of this asks about what the net torque is acting on the wheel, so we're just going to add up all of our torques. We do need to consider direction, though, okay? So for torque 1, we know that it is pulling in that direction, or we have a force in that direction, and so that's going to lead to rotation that way, which is the clockwise direction. Okay. What you can do if you're a little bit unsure of this is you can put your pencil down here along where the radial distance is and actually hold it where that pivot is, and then I would push in the direction of the force and see which way your pencil rotates. That's a great way to figure out the direction of the torque. For torque 2, all right, we're pushing at this point here. We're pushing up. That's going to cause counterclockwise rotation. So that means that torque 2 is counterclockwise. We're now going to add those two torques to get the net torque, or the sum of the torques, right? Same difference there. So it's going to be torque 1, which is negative 40, negative because it's clockwise, and that traditionally is the negative direction, plus torque 2, which is counterclockwise, so it's positive, and so we end up getting a net torque here of 25 Newton meters. So next question asks, is it possible for this wheel to be spinning clockwise? We keep in mind that our torque was 25 Newton meters and it was positive, which means that this was a counterclockwise torque. So can we be spinning clockwise while having a counterclockwise torque? The answer is yes. Okay, that would just mean that it is slowing down. Okay, this counterclockwise torque is going to cause a counterclockwise angular acceleration, but that doesn't mean we can't have a clockwise angular velocity. The wheel would just be slowing down. Part D asks if it's possible to be spinning counterclockwise. That also is possible. That would just result in a motion where the wheel is speeding up, because what we would have is we would have an angular acceleration and an angular velocity, both going in the same direction, and that results in speeding up. So we've talked a lot about mass so far this year, and you all have a pretty intuitive idea of what mass really is. But another way of thinking about mass is it really represents how difficult it is to accelerate an object. Okay, objects with more mass are more difficult to accelerate. There is a rotational equivalent to this, and that rotational equivalent is known as the moment of inertia. Okay, so moment of inertia represents how difficult it is to cause an object to accelerate angularly. All right, sometimes you'll also hear it called the rotational inertia, but either way, moment of inertia measures how difficult it is to make an object accelerate angularly. And we measure it in units of kilogram meters squared. So much like torque, it's not quite as simple as it's just a quantity. Okay, there's a few things that affect the torque. There's going to be a few things that affect the moment of inertia. The first is mass, and that makes sense. The more mass an object has, the more difficult it is to make it rotate. So all other things equal, okay, objects with more mass or the same size, shape, etc., are going to have a greater moment of inertia. The second is the radius or the size. Okay, increasing the size of an object increases its moment of inertia. So if you have two solid spheres, okay, with the same mass, but one has a greater radius, the one with the greater radius is going to have a greater moment of inertia. So that's the second thing that affects it. And the last thing, and the most important thing, and probably the most difficult thing to consider, is the distribution of the mass. And this is really the big key to moment of inertia. Okay, the more mass an object has further away from its axis of rotation, the greater its moment of inertia. Okay, so when we have a lot of mass far away from the axis of rotation, we have a much greater moment of inertia. And this is really key, okay, because this is going to allow us to explain why, depending on where an object rotates, its moment of inertia might vary. It's going to allow us to explain why the shape of an object really affects the moment of inertia. And we'll go through a few examples of this on the next slide, but this one is key. So you want to keep in mind that the further away the mass is from the axis of rotation, the point about which it's rotating, the greater the moment of inertia. So let's apply this idea of moment of inertia. The first question is, we want to explain why a sledgehammer is very difficult to rotate when it's held about the handle end, but much easier to rotate when it's held about the hammer end. All right? And this comes down to the idea that we were just talking about. If we hold it here, and this is the axis of rotation, we have more of the mass further away from the axis of rotation, as opposed to if we hold it on the hammer end. Okay, most of the mass is contained within that hammer, and so we have less mass far away from the axis of rotation. Therefore, it's more difficult, it has a greater moment of inertia when this is the pivot, because we have more mass further away from the pivot. For question B, we have three discs with equal mass and equal radius, but they have different shapes. We see for A, the mass is spread evenly throughout the entire shape, whereas B, there's a little hole in the middle, and C, it's basically just a ring along the outside. And we want to rank them, their moments of inertia, from least to greatest. So the least one is going to be A, and that's going to be less than B, which is less than C. And the key here is C has the most mass furthest away from the pivot. Okay, whereas in B, there's less mass further away from the pivot because the hole inside of it's smaller, it's distributed a little bit more, and A, that mass is distributed throughout, so there's the least amount of mass the furthest away from the pivot. Let's talk a little bit about mathematically calculating the moment of inertia. This is not something we're going to do a lot with. Okay, I'm going to show you some formulas on this slide and the next slide. They're not even on your equation sheet. If it's in a problem, you'll just be given this formula because it's not an emphasis in this class or for the AP exam. But the basic formula for the moment of inertia of an object, which we tend to call a point mass, okay, meaning that it has no volume, it's just located at a single point, revolving about some axis, meaning it's traveling in a circle, is given by this equation here, mr squared. Okay, the mass of the object times r, the radius of its circular path squared. All right, so that's what we're going to use if we just have some mass. If we have specific shapes that are rotating or spinning, we have a whole bunch of formulas that are listed on the next slide. You do not need to know these formulas. You will never need to memorize them. If you're asked to use it on a test, you will simply be given that shape formula. Okay, so we're going to do a little bit of practice with this. I think it's worth practicing calculating it. However, it's not going to be a major emphasis of this class. The more important thing is going to be the conceptual understanding of moment of inertia and what really affects it. That will be a key emphasis of this class. All right, so here we have a few different shapes. You notice for each one we define what the axis of rotation is, what the actual shape is. So we have a point mass, some hoops, okay? It's continued on this page with a few more shapes, solid sphere, hollow sphere. One thing that you might want to notice here is we see right here this conceptual difference between a solid sphere where the mass is spread throughout and a hollow sphere. Okay, the solid sphere has a smaller moment of inertia, assuming the same mass and radius, because more of the mass is closer to the axis of rotation, whereas a hollow sphere, the mass is all on the outside, and so it has a greater moment of inertia. We're going to go ahead and run through two quick practice problems. Like I said, I want you to have a little bit of practice calculating this, but the conceptual understanding is the main thing here. So we have a bowling ball, which is a solid sphere here with a mass of 7 kilograms and a radius of 11.5 centimeters that pivots about an axis through its center, and we want to calculate its moment of inertia. So we find that the moment of inertia for a solid sphere is 2/5 mr squared. Okay, and so it's going to be 2/5 times the mass of the bowling ball, which is 7, times r, 0.115 squared. And so we get that the moment of inertia for this bowling ball is going to be 0.03703 kilogram meters squared. Okay. Second part, we have a system consisting of a solid disk here with a box sitting on top of it. So there's two objects. All right, and we want to calculate the moment of inertia of that system. So I'm going to take it one step at a time. When we do have multiple objects, we need to calculate their moments of inertia individually and then combine them. Okay, we can't just call it one thing because the box is not a disk. So we can't say it's shaped like a disk. We can't use 1/2 mr squared, which is the moment of inertia formula for a solid cylinder or a disk. So for the disk, we're going to do 1/2 times 50 times its radius, which is 3 squared, and we find the moment of inertia of the disk is going to be 225 kilogram meters squared. The other shape we have here is a box. Now the box itself is not rotating. The box is simply a point on this circle that's going around, or on this disk that's going around in a circle. So we're going to treat the box as a point mass. Whenever we have an object that's just sitting on a rotating object, okay, the box itself is not rotating, it's sitting on a rotating object, we're going to treat it as a point mass. So its moment of inertia is going to be mr squared. So we take the mass of the box, which is 30, times r, which is the distance from the axis of rotation, or the radius, squared, and we get that the moment of inertia for the box is 120 kilogram meters squared. We can combine those two numbers to get the total moment of inertia here for our system, and it's going to be 345 kilogram meters squared.